Welcome to this module of computer-aided power system analysis. Till the last lecture, we have discussed the details of the GSLF process, that is the Gauss Seidel load flow analysis. In this lecture, today we will be looking at an example of the Gauss Seidel load flow analysis involving all the issues, that is the generator reactive power limits and let us say a presence of PV buses as well as the presence of PQ buses. So, then before we do look into the example, let us first try to recollect that what we have discussed very briefly, so that we can immediately connect our discussion with the example of today. So, what we have discussed is the Gauss Seidel procedure. So, we say that Gauss Seidel GSLF algorithm. We will not be discussing all the mathematical details, but just for a simple recollection that what we have done. So, first in that we take a flat start, and when we said that we are taking flat start means that for these generator buses the voltage magnitudes would be equal to their specified voltage, the angles would be 0, and for all the load buses the voltage magnitudes would be 1 per unit and their angles would be 0. And after that what we do, that we take iteration count, or rather initial count something k is equal to j is equal to 1. Now, here again we are discussing n bus M machine system. First one is slack bus, this is just our nomenclature, and then 2 to m PV buses, and then m plus 1 to m plus 2 to n PQ buses. So, that is the nomenclature we are using. So, then what we do is, then after that for all, for I is equal to 2 to m, we do the following. First we calculate Q. We have already looked into the expression how to calculate Qi using this initial voltage magnitudes and angle, and then if Qi is Qi max, that is within the limit, then we only calculate the bus voltage angle, keeping the bus voltage magnitude, or rather I should keeping Vi is equal to Vi specified. Vi stands for the magnitude of the bus voltage I, and Vi specified is the magnitude of the specified bus voltage of bus I, when bus I is a generator bus. And if either Qi is greater than Qi max or Qi is less than Qi mean, then we calculate both Vi and theta I, where theta I denotes the bus voltage angle of bus I. And then what do we do for, so this is third, so for, then what do we do, we for I is equal to m plus 1 to n, that is for load buses, we calculate both V I and theta I. Then what we do is, after all these calculations are over, then we calculate E I is actually, we should put this j all at j, this should be j, this should be j, this should be j, and we calculate also this should be j, it should be j. J with a superscript denotes that we are calculating these quantities at the iteration count j, that is we are calculating all these quantities at the jth iteration. So, we calculate then we calculate E I j, or as V I j, remember this is a magnitude, these are complex quantity into V I j minus 1 for all I is equal to 2, 3 to n. Then what we do, we calculate E max is equal to max of E 1, E 2 to E n, then check for convergence, or rather we should write more succinctly. If converged, stop, else j is equal to j plus 1 and go to step 3. This is what we have basically discussed here. Of course, as you can see, we have not included all these equations, because all these equations we have already calculated, we have already mentioned in our last classes. So, then therefore, here we have simply omitted all these necessities. So, this discussion was just for a very quick recapitulation of the very basic Gauss Seidel load flow process. So, with this, now what we will do is, we will now look into an example. So, an example we are looking into. So, we are now taking an example 5 bus system. So, what we have got? So, we have got bus 1, 2, 3, 4, 5, and here in this system you can see that there are 3 generators at bus 1, bus 2, bus 3. You can also see here that according to our own nomenclature, or according to our own convention, we have put all these 3 generators in the first 3 buses. So, at bus 1, bus 2 and bus 3, these generators are connected. Bus 1 generator is is actually assumed to be the slack bus, and bus 2 and bus 3 buses are actually the PV buses. And then what we have? We have also got 2 more buses, bus 4 and bus 5, these are nothing but the PQ buses, and at these 2 buses there are PQ loads. So, this is a very small 5 bus example system having more than 1 generator and more than 1 PQ bus. So, it has got both slack bus, PV bus and PQ bus. So, this example will suffice us to demonstrate the working of this basic GSLF load flow analysis. So, now this is the data. So, here we are simply writing down the data. So, bus number 1, 2, 3, 4, 5. Here in this data we have denoted type. Type is 1, 2 and 3. So, type 1 denotes that it is a slack bus, type 2 denotes that it is a PV bus, and type 3 denotes that this is an PQ bus. And we have already discussed in the last slide that bus 1 is taken to be the slack bus. So, that is why its type is denoted as 1. Bus 2, 3 are considered to be the PV bus. So, as a result their type is taken to be 2, and then subsequently bus 4 and 5 are considered to be PQ bus. So, as a result their type are taken to be 3. Now, in this example for bus 1, bus 2 and bus 3, that is for these 3 generators, the specified voltage is 1 per unit, everything is in per unit here. So, and of course, and so then therefore, we have got 1. And for bus 4 and bus 5, we have already discussed that when we do take the flat start for bus. So, for these load buses, we do take the flat start as magnitude 1.0 per unit and angle 0. So, then therefore, here also we have taken magnitude V to be 1 and 1 for bus 4 and bus 5, and for all this and for all these buses there are angle 0. Now, you can see that for bus 1 there is basically nothing else is actually pre-specified. Now, because bus 1 is a slack bus, so then therefore, there are only 2 quantities which are specified, that is bus voltage magnitude, that is 1 per unit, and this angle theta is equal to 0. And for bus 2 and 3, because these are PV bus, so then therefore, their voltage magnitudes are specified, and both these voltage magnitudes are 1 and 1. And their real power generation by them are also specified. So, we have got for bus 2 this is 50 megawatt, and for bus 3 this is 100 megawatt. And for bus 4 and bus 5, because these are not a generator bus, so then therefore, there is no PG here. And for QG there is no such specification. Please remember that when we do specify any quantity at any bus, we do specify Q only for the load buses. So, for no generator Q is actually specified. So, then therefore, this column is 0. Now, bus 4 and bus 5 are nothing but the load buses, and for this load buses we have got P load is 115 for bus 4 and P load is 85 megawatt for bus 5, and similarly we have got Q load 60 and Q load 40 for bus 4 and bus 5. Please remember PL and QL, these are 0 for bus 1, 2, 3 because these are generator buses. And then what we have is, although these are not necessary, I mean, now what we have is for bus 2, for bus 2 and bus 3, we have got Q mean and Q max. Q mean is minus 500 and Q max is plus 500. And bus 4, 5 and I mean these are not necessary, but somehow they have come anyway. And we have taken base MVA to be 100 MVA. So, then therefore, in per unit this PG would be 0.5, and for bus 3 PG would be 1 per unit, and for bus 4 PL would be 1.15. So, then therefore, injected power at or rather injected real power at bus 4 would be minus 1.15 pu. Similarly, injected real power at bus 5 would be minus 0.85 pu. Similarly, injected reactive power at bus 4 would be minus 0.6 per unit, and that at bus 5 would be minus 0.4 per unit. And injected real power at bus 2 would be 0.5 per unit, and that at bus 3 would be 1 per unit. And for bus 2 and bus 3, Q mean would be minus 5 per unit and Q max would be plus 5 per unit. So, everything we should convert into per unit, because we have already discussed in the first or second lecture, we do our calculation everything in per unit to eliminate the problem of this turns ratio of the transformers. Now, this is basically the line data for the 5-bus system. So, it is branch number 1, 2, 3, 4, 5, and for example, for each branch number, that is what is basically the from bus and the 2 bus. So, then basically these are nothing but the terminal 2 buses of each line, and for each line you have given R, X and B by 2 in per unit, and none of the line is equipped with any transformer which has got tap changer. So, everything is here in per unit. R stands for resistance, X stands for inductance, and B by 2 we all know that this is nothing but the shunt, half line shunt charging susceptance. And there is small correction that there is some printing error here, there is a rather some kind of typo here. For line connected bus between bus 3 and 4, that is for branch number 4. For branch number 4, these actual values are 0.024, x is equal to this and this. So, please kindly note this correction. So, now initially what we do is we do not consider any reactive power limit at the generators. In fact, that we have already ensured by taking the two high value of the Q min and Q max, because here you see we have taken this Q min as to be minus 500 MVAr and Q max to be 500 MVAr. So, these are pretty high values. So, when we are considering pretty high values of this minimum and maximum, effectively essentially we are saying that there is no reactive power violation at any bus. So, with this we start our iteration. So, then what you can see that in the iteration, although we have calculated this, but now what we have done. So, in the first iteration, as we have said in our normal algorithm, as today we have just now recalculated or rather recapitulated our basic algorithm, what we have said that first for this two generators we will be first calculating this Qi. So, we have calculated Qi for bus 2 and bus 3 because these two are these two generators. Now, our limit is minus 5 per unit to plus 5 per unit. So, obviously, these two values are well within their limit. So, then therefore, their voltage magnitudes are maintained at 1.0 per unit, which is their basically the specified value, and their angles are recalculated. And for this bus 4 and bus 5, both this voltage magnitude and angles are recalculated, and error by that basic process of error we have calculated. You see that this is quite high. So, we go back to the second iteration, again we recalculate this Qcal and for this bus 2 and bus 3. Now, these are quite changing, but then still they are well within this limits for bus 2 and bus 3. So, again this bus voltage magnitudes for these two buses are maintained at 1.0 and their angles are actually getting changed. Remember, when you are calculating these angles in our actual calculation in our algorithm, when we are calculating these angles, those angles would be calculated in radian, but then here when we are actually reporting these values, we are writing in degree for our convenience of understanding. And for bus 4 and bus 5, these are the standard load buses. So, then therefore, we are simply calculating their voltage magnitude and angle. So, then we are again calculating the error. So, this error still is pretty high, and but although it has reduced, but still pretty high. So, we go on at iteration 3, again we calculate Qcal, it is still minus 0.2 and plus 0.5, these are, and again these two values are still within their limits, well within their limits. So, their voltage magnitudes are maintained and the angles are calculated, and for load buses voltage magnitudes or angles are calculated, error has reduced, but still not. So, we keep on doing these calculations for iteration 4, iteration 5, iteration 6. You can see from all these results that for all these iterations we have first calculated this Qi for both these generators, and everywhere we are finding that their values are well within the limit. So, then therefore, their magnitudes are maintained at 1.0, only their angles are being calculated, and the voltage magnitudes of both the load buses are being updated, both the angles as well as voltage magnitudes. Error is decreasing, although it is decreasing pretty slowly, but although it is getting converged slowly but gradually. Now, if we keep on doing this and we have kept our threshold, that is epsilon, that is equal to 10 to the power minus 12. So, if we keep on doing this calculation, in fact we need to write an computer code for this. So if we keep on writing these codes, and so if we keep on doing this calculation, so this entire process converges after 69 iterations, that is this error comes below this value 1.0 e to the power minus 12, and then these are the final results. So in this final results, what we have said, so we have simply given V theta, that is the voltage magnitude, angle, injected power, and injected real power, and injected reactive power at all these buses. And here we are saying that it is without generator Q limit, and we are saying that because we have taken these limits to be pretty high, minus 5 per unit to plus 5 per unit. So we can see, because there is no generator Q limit, so then therefore for bus 2 and bus 3 voltage magnitudes are maintained at 1.0 per unit, although their angles are changed, are not equal to 0. For bus 1, that is the slack bus, so its magnitude is retained at 1.0 and angle is 0. In fact, this angle is actually acting as the reference. So then therefore all these angles are actually being calculated with respect to this angle, and this magnitude of these voltages are this, and this angles are given. Now these are the injected power at bus 1. So you see, if we look at this injected power at bus 1, 2, 3, 4, 5, at bus 2, please recollect, we have shown in our data that our real power injection is 50 MVAR. So then therefore injected power would be 0.5 per unit, and bus 3 our real power generation is 100 MVAR, 100 megawatt, sorry, it is in this case 50 megawatt and it is 100 megawatt. So then this real power injection would be 0.5 per unit and 1 per unit. And at the load buses at bus 4 and bus 5, please recollect that this load was 115 megawatt and 85 megawatt for bus 4 and bus 5 respectively. So then therefore this injected values would be minus 1.15 and minus 0.85. And for load buses, please recollect that this load was 60 MVAR and 40 MVAR respectively at bus 4 and bus 5. So then therefore in our parlance, or so then therefore this injected reactive power would be minus 0.6 and minus 0.4. And for bus 2 and bus 3, after this load flow is converged, we have calculated this reactive power injection for bus 2 and bus 3 after this value is concerned. Calculated. Now how did we calculate this reactive power injection? Simple, that we are using that expression that Qi is equal to summation k is equal to 1 to n Vi Vk Yik sin theta I minus theta k minus alpha Ik, that is the standard expression. So we calculate this Qi, and so from this here you see that bus 3 is actually giving reactive power to the system, and whether bus 2 is actually absorbing reactive power from the system, and bus 1 is giving 56 megawatt real power to the system, and it is giving 26 MVAR. Now if we look at this total load and total generation, so total load was 200 megawatt, 1.15 and 115 and 85. So total load was 200 megawatt, and the generation by these two PV buses was 150 megawatt. So then therefore a rest of 50 megawatt plus some losses should come from the slack bus. Indeed it is the case. So here we can see that this slack bus, it's actually generating or rather supplying 56.743 megawatts. So then therefore this 50 megawatt is basically due to this shortfall, right, and rest, that is 6.743 megawatt, is nothing but the total loss in the system. So then if so then therefore here we can see that my total load was somewhere 200 megawatt and my loss is 6.743 megawatt. So then my loss percentage is somewhere around 3.5 and 3.3%, which is the standard value, which is basically the typical value in a transmission system. Similarly, if we look at this reactive power, what we can find is that this total reactive power load is 100 MVAR, and out of this somehow because of this bus 2 is actually, so now here our total reactive power load is 100 and basically 118 point something MVAR, and bus 1 and 3 they are together generating these actual values. So now what we do is we go to the next case. Now we consider this limit on bus 3. Now when we consider this limit on bus 3, now what we say that in our generator we have got now a limit of 50 MVAR. Now what we have found is that for generator 3 it is actually generating 68 MVAR. Now we are considering that this bus 3 is a generator and it can only supply up to 50 MVAR, not more than that. So then therefore this bus 3 will now be shifted from PV to PQ bus. So now what will happen is, so now what we do is again we start this calculation. So in the first iteration you see now basically the limit for bus 3 is minus 5 to plus 0.5, but then what happens that in iteration 1 and 2 there is, for bus 2 there is no limit because its limit is still minus 5 and plus 5. For bus 3 it is minus 5 and plus 0.5, but in first two iterations this reactive power generation or rather the calculated reactive power in bus 3 are well within the limits. So as a result the voltage magnitude at bus 3 is maintained at 1.0, and although their angles are being calculated, and for bus 4 and bus 5 we are doing the similar calculations. From iteration 3, at iteration 3 the calculated reactive power at bus 3 becomes 0.5142 per unit, but my limit is 0.5 per unit. So therefore this is exceeding. So then Q cal is more than Q max, so it is exceeding. Because it is exceeding, so then therefore this generator won't be able to supply 0.5142. Remember this 0.5142, remember this particular value is indicating that this generator has to inject 51.42 MVAR reactive power to the system to maintain its voltage at 1.0 per unit, or rather to maintain the voltage magnitude at its terminal at 1.0 per unit. But because it is only supplying 50 MVAR, so then therefore its voltage magnitude cannot be maintained at 1.0 per unit because it is supplying less amount of reactive power to the system as compared to what is actually required. So then therefore its voltage magnitude will actually come down from 1.0 per unit to some value which is lower than 1.0 per unit, and that is indeed the case. So in the first two iterations this bus voltage magnitude at bus 3 is maintained at 1.0 per unit, but from bus 3 but at iteration 3 it has now reduced from 1 to 0.9955 per unit. So it has now reduced, and these angles and etc. are being calculated. Errors are also getting reduced. So if we keep on doing this calculation again and again with this same value of limit of this or rather of the same value of this convergence criteria, that is 1.0 into 10 to the power minus 12. So then this particular algorithm converges in 66 iterations, and now for comparative purpose we have shown the results without generator Q limit and with generator limits side by side. So we can see for bus 3, because this reactive power limit was being exceeded, so its reactive power injection is only maintained at 0.5 per unit, right. So it is being maintained at 0.5 per unit, and but its voltage magnitude has reduced from 1 to 0.9825 because of the simple fact that this particular generator had to supply 68 MVAr to maintain its voltage at 1.0 per unit, but because of its restriction it is now being able to supply only 50 MVAr. So, as a result its voltage magnitude will now come down from 1.0 per unit to 0.9825 per unit, and all the other voltage angles and all the other load buses are, everything is calculated. Now, here is an interesting point. If we look at this P inch, that is injected in, that is if we look at this injected real power, we can see that this total amount of injected real power is more than the total amount of load. It has to be, because basically the total amount of generation should be load plus loss. In the first case, when there was no generator Q limit, total amount of generation was 206.743 megawatt, where there was load is only 200 megawatt. So, then therefore, basically the total amount of generation is more than the total amount of load, and our loss is 6.743 megawatt. In the second case also, my load is 200 megawatt and my total generation is something like 200.6979, 206.979. So, again this total amount of generation is so again here also total amount of generation is more than the total amount of load, and my loss is 6.979 megawatt. But if we look at this Q injection by all the generation and the load, there is a very surprising thing. If you see my total amount of reactive power which is being absorbed, now here when I say minus, because these are injected value which are minus, so then basically they are physically being absorbed. So, this amount of reactive power is physically being taken away from that bus. So, this value is something like 118.519 MVAr, but total amount of reactive power which is being injected, or rather which is being generated by the generators are only, here it is 26 and it is 68. So, it is coming out to be something like 94 point something, or let us say roughly 95 MVAr. So, here the total amount of generation by the generators, or rather total amount of reactive power generation by the generator is only 95 MVAr, but total amount of reactive power which is being taken away from these buses, or rather we can say that the total amount of reactive power which is being or rather total amount of or effective reactive power load is something like 118. So, generation is less than the total amount of reactive power load. So, what is happening here? The answer is very simple. Answer is that each of this line has got shunt charging susceptance, because we have taken B by 2. So, because of this availability of the shunt charging susceptance, this shunt charging susceptance, which are nothing but capacitors, they also do generate substantial amount of reactive power. So, then therefore, this shortfall, that is 118 minus 95, so roughly 23-24 MVAr of reactive power is actually being generated by this shunt charging susceptances of the lines. Same thing also here. Here our total amount of reactive power load, effective load is coming out to be something 100.4 MVAr, and but this total amount of generation is only by the generator is only 83. So, the rest, that is 17 to 18 MVAr of this reactive power is being generated by the shunt charging susceptances of the lines. Now, here you can see that as compared to this case, the first case without generator Q limit, the overall voltage profile is lower, that is with generator Q limit. If you look at this voltage magnitude profile, is it is actually lower. For bus 2 this is 1 on 1, but for bus 3 and 4 5 these are actually lower. So, then therefore, overall voltage profile in the second case when there is a generator Q limit is lower, because this voltage profile is lower in the second case. So, then therefore, total amount of reactive power generation by the lines is also lower, because for any shunt charging susceptance the amount of reactive power Q is given by V square into omega c, although omega c is remaining constant, but because V, which is nothing but the magnitude which is being reduced. So, then therefore, the total amount of reactive power which is being generated by the lines are also being reduced. That is precisely why here in this case when there is a limit on the generated Q generation, the total amount of reactive power which is being generated by all the lines combined together is only 17 MVAR, whether here when there is no generator Q limit, here it is roughly equal to 25 MVAR. So, this completes our examples. So, here in this lecture today we have looked into the an example of the GSLF load flow. We have taken a simple 5-bus system in which slack bus, PV bus and PQ bus all are available, and we have also considered two cases. In the first case where there is no generator reactive power limit, and in the second case there is a generator reactive power limit, and we have shown the detailed calculation procedure and ultimately compared their results, and we have also discussed that how these results are making a lot of sense. So, from the next lecture onwards we would be taking the other aspects of this load flow analysis. Thank you.